Okay, so I will be getting you that study guide later today. You'll be on the lookout for that for an exam a week from today. The last part of that will probably be Dijkstra's. So be thinking about and ready to basically do what we've been doing yesterday, as well as what we'll be continuing to do today. And other than that, I don't know if I want to schedule a first review for Wednesday or Thursday of next week, but we can make that decision probably early next week based on how we feel about the content that we've been going over. My hope is that this material is a little bit more straightforward than the first exam's material. But I leave that up to you and the class as a whole to decide. Questions or concerns before we dive into new material? Okay. We were working on another example of Dijkstra's algorithm. So in case you haven't had a chance to do a little bit, let's take a few minutes at the start of class to work through this example. If you had a chance to work on this and think you have an answer, double check your work. You can also talk to your neighbors, work through this together, or check your work with those around you. Are there any clarifications I can make with regards to what we're doing, how to get started? Let's getting started. What's the first step here?
Wouldn't it be going to D because D has a cost of 1?
Yeah, so the first thing we should do is expand this initial vertex. So we're going to mark it as known. Path is just through itself, so we don't need anything there. But we're going to update these question mark infinity integer.max value costs to anything where we can directly reach it as a neighbor of A. So we can directly get to D and C. So if the path to D is less than or equal to 1, the path to C is less than or equal to 2. Those are the only direct neighbors of A. There's an in edge from B to A, but we're only considering out edges here, places we can get to from A. So those are the updates that we make. And then, as mentioned, we're gonna take the minimum cost here of unvisited nodes. So everything without a y in this known column, we're going to find the minimum value in the cost that's not solidified. So that's this one, that's going to become the next node that we expand. So that solidifies the value of D as a cost of 1. The backtrack path for D is through A. And we mark that as known. We're then going to add every edge out of D. So there's an edge out of D to B with cost 5. The total cost of getting to D is this cost right here. We're going to add this cost to the edge weight from D to B, which is 5, giving us 6. So our new best path to B is 6. Can we get to E?
Yes.
Yes, we can. The total cost of getting to D plus the edge weight 1 from D to E tells us this is less than or equal to 2. Can we get to F? Yes, we can. Edge weight 6 plus the 1 to get to D. This is less than or equal to 7. And can we get to G? Yes, we can. So now we can get everywhere from D. So the question is just, is there a better way to get to any of these than directly through D? So the rest of this entire process is going to be proving that. Is there any better way than through D to get to any of these other nodes? But we will start by taking the minimum cost of unvisited nodes, which is 2, but we have a tie. We can either choose C or E here. It does not matter the order in which you do this. Anyone have a preference?
I would for E, let's be honest.
Let's go with E. Sure, it does not matter which one you do. So from E, we're going to solidify E as now this is locked in as a 2. We're visiting E. The backtrack from E is through D. So we finalize that coming from D. I can actually write where all of these are coming from as we do this as well. This is all through D. And some of these will change as we go. But now we look at every out edge of E, and we see there's only one going to B. The total cost to E is this 2. We're going to add this 2 to the half cost of E going to B, which is 1. And then we ask, is that 2 plus 1, 3, less than this 6 that's already stored here? Since it is, we're going to update this value from less than or equal to 6 to less than or equal to 3, and backtracking not through D, but through E. Question?
The path to C and D.
No.
That is for A, wasn't it? Yes. That's a great point. Okay, that was the only out edge from E. So we finished that, but yeah.
Quick question, I forgot, are you recording
Yes.
now for the, okay, just check.
Want to be sure of that. This is important to look back on. All right, looking back through these, the minimum value is still 2. There is no way that we would leapfrog going from E that was tied with C to any other node. We're guaranteed to be doing either E then C or C then E. Everyone see why that is intuitively? There's no way to update something to a value less than what was the minimum before.
We lock in B since we explored all incoming edges already.
We probably could, but we want to do it when we visit it, just to be sure that we visited it. But yeah, this will be 3 for exactly that reason. We've explored every edge into B, so this cannot be updated again.
Yeah.
It's just a matter of when we visit it, because we have to visit anything that is less than before we do that. But yeah, there's no way this is less than. This is equal to 3, which is delay when we visit it. To be sure. All right, going back to C, we'll lock in C at a cost of 2. We're gonna look at every outgoing edge from C. We get D and F. For D, we've already visited it, so there's no way we can possibly update this. We've already visited it. F, on the other hand, was less than or equal to 7, but we can find the path, the total path cost to C plus the edge from C to F. 2 plus 2 is 4. 4 is less than 7. So we're going to update this less than or equal to 7 to less than or equal to 4. And now instead of pathing back through D, we're pathing back through C. And now we visited C, so we can do that. Looping around, minimum path cost here is 3 for B, so we'll lock that in. We're gonna explore every out edge of B, just goes back to A, which is already visited. So no further updates to the table, we just visit B, lock in that value, and we're done. Looping around, we find the minimum of just a couple that are left. We have F. So we'll lock in the 4. Visit F and look at every outgoing edge. From F, there is just 1 that goes to G with cost 10. So we'll take the total cost of getting to F, the 4, plus the 10 that is the edge weight from F to G. We get 14. Is 14 less than the existing best path G6? It is not. So we will not update that value. That's the only outgoing edge. So we're done with this. We loop back around. We find G. And since this is the last vertex, we just lock in that value and visit. And now that there's no further unvisited node, we would lock in this table as being complete. And this is the one-to-many shortest path from A to every other vertex in the graph. Any questions on any of this process? Show of thumbs maybe, and how does this feel? Would you be able to do something like this on an exam?
I think it's decent so far.
Yeah.
Actually,
As long as you're not like really cruel about it.
just kind of wanted to see what the order of the slide ended picked this time.
Yeah, everything should look exactly the same except for whether we choose that C or E when we had that tie of 2. We could have done C first. But it does not matter. We'll get the same answer regardless.
All right.
All right, we're good with everything that's on the board. We can memorize this if we want to verify that what's on the slide is exactly what was here. It should be.
Okay, yeah, I get it. It's not. So that is really crazy.
So that works. That's very nice.
Not-
We ready for another example?
Oh, let's do this thing then.
All right. I came up with a weird one.
That is weird. Okay.
So you can draw this out if you'd like. The question that I have for people is basically the best cost so far to this destination Y. How does that proceed? So feel free to draw out this as we go, and we will go over it in a couple minutes. We can label these as well. Yeah,
Would be best also. Like every iteration is best.
yeah. If you came up with the total path cost on every iteration of Dijkstra, how would that proceed?
Oh, yeah, that table. Let's see. Uh, let's put this in. What is it?
All right, we have something. Would like some more time to work? Let's just quickly fill this in. I think intuitively, it makes sense that we're gonna be updating this value every single time.
Yeah,
Hopefully people can see that. This 90 is gonna be bested by this 1 plus 80, which is gonna be bested by this 1 plus 1 plus 70, which is gonna be bested by 1 plus 1 plus 1 plus 60. Until we find the optimal path, which is the absolute longest possible path by number of edges. Happens to be the least cost by edge weight. So we start by marking our source as visited. Cost is 0. There's no such thing as a backtrace. We started there. We want to now update with all neighbors of x. So y has a cost that is less than or equal to 90. A has a cost that is less than or equal to 1. And the backtrace for both of these is through A for x. Okay, what is the minimum cost?
1.
A has a minimum cost of 1. Great, we're gonna visit it, lock it in. Where can we get from A? We can get to Y with cost 80. So the 1 total cost of getting to A plus the 80 cost of getting from A to Y is a total of 81. So we're gonna update this to be 81. Backtrace from here is now not through X anymore, but it's through A. We could also get directly to B with cost 1 to get to A plus the edge weight 1 from A to B. That backtrace is through A at that point. So we look at the minimum and we see that it is 2. So we can lock in that value. Look at every edge out of B. We can get to Y with cost of 2 to get to B plus 70 to get from B to Y. So that is 72. We update our backtrace through B rather than A. We can also get to C with total cost 2 to get to B plus 1 to get from B to C. Looping back around, find the minimum and the cost. That is C, so we're going to lock that in and visit it. From C, we can get to Y with the cost 60, so the total cost of getting to C, 3 plus the cost 60 gives us 63. We're going to update Y to be 63. Backtrace now through C. Sorry, this should be B. We can also get from C to D with total cost 3 to get to C plus 1 to get from C to D. So we add that with a backtrace through C. Looping back around, find the minimum, that's 4, we'll lock it in. Here, outgoing edge from D to Y costs, total cost of getting to D plus the edge weight from D to Y is 50, so we get 54, and this backtrace is now through D. Looping back around, this is the minimum value. So we can lock it in. And we're done. So visually now we can see that the shortest path to y, we're looking at paths of length 1, paths of length 2, paths of length 3, paths of length 4. And so we only update when longer paths, in this case, are better than shorter paths in terms of number of edges. Questions on this example? I just wanted to pick a kind of extreme example to show what that looks like. And why an assumption like the minimum number of edges is more likely to be, or couldn't possibly be, the longest possible path to y couldn't possibly be the shortest edge weight. In this case, it is. So we can never make that assumption. All right, any questions on any of this before we move on? Okay, that is exactly what we saw. Interesting question. In terms of complexity, is this expensive? What do we think with regards to this algorithm? When we see that we have to look at every possibility here,
It is fairly expensive, honestly.
is there any way we could do this better? And or is there any way that we could think about this concept of expensive? What is the limit of how much work we have to do here? What's that? What's the variable that is the worst case amount of work that we're doing?
Like we're going to be checking through like, oh wait, no, sorry, what were we gonna say? Please go ahead.
We're definitely looking at the edges, right? Because we're processing each edge at most once as we go through this process.
Yeah.
We're never, when we see the 90, we're never going back to the 90. When we see the 1 from X to what was A, we only ever process that once. So each edge is seen at most once. So it's based on the edges. So even though this seems like a lot of work when we go through this in practice, it is based on the number of edges. So let's break this down into finding the actual efficiency here. And it really depends on how the priority queue is implemented. So you're imagining, if you're going back to this and thinking about it in terms of code, how are we doing things like finding the minimum value seen so far? We talked yesterday about the concept of a heap and how, in this case, the minimum value, if we store this as a min heap, would be the root of that min heap. So we can find what the minimum is in constant time. Yeah.
So there'd be a
No, this would just be the cost array, like the vertical cost part of that. You'd store all of those costs in the heap. So if we store this not as a heap, but an array of vertices, then we would actually have to go through every vertex for every vertex, and then we would be doing something for each edge. So b squared plus e. And if you implement this as a Fibonacci heap, and that's just a slight variation on the concept of a heap, but it's not too much harder to actually implement, then we can get this all the way down to e log b. So the actual process you use to implement this is significant in terms of reducing what would be a brute force complexity for solving the problem, but that heap just drastically reduces the concept of that, because you would end up having to, if you're using an array of vertices, then yikes. It's a lot of work. Does that make sense to people? Why using a heap here saves a tremendous amount of time?
Yes.
So that's Dijkstra's algorithm. In practice, it's very efficient. It works extremely well. but it doesn't handle negative edge weights. Maybe we can take a second to think about why that is. Why would Dijkstra's struggle when our graph has negative edge weights? Yeah,
There's a name very bad. It could draw a higher yield.
yeah,
Banking on solidifier. Further down, which has
yeah, we're making a very important, let's go back to like example two's solution here. When we solidify one of these costs, we know there's no way we're ever going back to it. We've found the shortest path to that. That assumption is not valid if there are potentially negative edge weights. If we could say, for instance, that what's an edge we can change here that would drastically change how that. If we do the 10, we'd still look at it from F to G before, so we need to go back to something that we visited before, making that path cheaper. I'm thinking E to B here. If we turn this into something that's -1, then no, there's no easy other way to get there, so we still would have gotten there.
Yeah,
We need to go back to something we visited before.
well, something from D.
C to D. If this became -2, as an example.
the cost would be 0 and that would be weird.
Yeah, so from A, we're sorting these by cost. We first visit D and we never go back to thinking about a better path to D because we've already visited it. But there could be a path that starts out more expensive that becomes less expensive through a negative edge weight. And that would cause us to have to go back to every single one of those vertices for every possible edge or sequence of edges. So this process it's going to take a heck of a lot longer. And you may find that it in fact never converges, which is a problem. Thoughts on that? Hopefully that's a little bit of the why, and that makes a little bit of sense as to when we do solidify this cost, we're making an assumption that that is the best possible path there, and it cannot be updated. And that is true as long as there are no negative edge weights in the graph. That assumption is valid. But as soon as you add negative edge weights, that's not good. We lose our ability to ensure that our assumptions lead to the optimal answer. So what would need to change? How could we handle negative edge weights? Yeah, we need to think about a bit more context about edges. So the way we're going to do this is we add edges that we see to a frontier. And this is just kind of think of a frontier as neighbors of things that we visited. And we're going to, just like we did before, update the best path seen so far from source to destination. And we'll see how that works. There is still one very important assumption that we need to make about the underlying graph for this to work, and that is that we can't have a negative weight cycle, meaning that the total cost of getting from a node, a vertex, back to itself can't be negative. If that is the case, then we can forever find a better and better and better and better path. This will still not converge. Yeah, we could have a cycle of total weight 0, which would mean the number of times we do this doesn't matter and it won't change the score. But as soon as it's negative, every time we iterate the cycle, we are subtracting something from the total cost, which means that cycle is part of any path from a source to a destination that ends up, the limit of that is negative infinity, because we could iterate that cycle an arbitrary number of times. So each iteration, we're going to decrease the cost of the shortest path. The answer would be negative infinity. That would be a problem. The algorithm would never terminate to produce the result of negative infinity. So we'd have to be able to identify that there is a negative weight cycle at any way that we could get to any part of that cycle within a source destination would create a negative infinity. We'd have to add that. And analyzing and finding negative weight cycles on a graph is already a more expensive problem than this. In fact, we can show that finding a negative weight cycle in a graph, we'll talk about this in a couple of weeks, is an NP-complete problem, which means it is basically intractable. As the graph scales in size, finding those negative weight cycles would become harder and harder and harder to the point that it is impossible to do in a reasonable period of time. So if a negative weight cycle exists, then we'll just return failure from this. But this is the introduction to Bellman-Ford, because Bellman-Ford is the shortest path algorithm for graphs for negative weight edges, but not negative weight cycles. So yeah, Bellman-Ford solves what we're going to call the single source shortest path problem in the general case where we may have negative edge weights. So pros of using Bellman-Ford is it works on more graphs. If you have any reason to believe that your graph structure could have negative edge weights, you will want to implement shortest path with Bellman-Ford. If you can show that there is no way that any edge could ever have a negative weight, then Dijkstra's is more efficient. So you should choose that. Yeah.
What are some examples of negative?
But like bandwidth.
Potentially, if something's going in the opposite direction, you could say that the edge weight is the amount of data being sent from A to B. If there's something being sent from B to A, then that could be a negative edge from A to B. We'll see an example of this when we talk about flow networks later on. But this could also be something like a bill being paid. It is a negative edge from your bank account to something else.
Would something like input delay be something like that?
Possibly. Whenever you could have positives or negatives, if it's all negative, you can just invert it to be positive and work. Although that has its own special problem that I won't get into. Because then instead of finding the minimum path cost, you'd be finding the maximum path cost. And I'll talk about this later, but that problem is actually also intractable. So yeah, only use Bellman-Ford if there are negative weights in the graph or could be negative weights in the graph. So I'll give you an example here of a graph. Here's a graph that has some negative edge weights. Yeah, that kind of got stretched a little bit.
What exactly?
Those are infinities on the
Okay.
vertices.
Well, that's
We have vertices S, T, X, Y, and Z. So take a second look at this graph. And if the goal is to path from S to Z, what's the shortest way to get there? I see 6 and -4 for a total of 2. That's not bad. It looks like S to X might be a little bit harder. Still not too bad. All right, so process we're going to go through here. We're going to first look at every outgoing edge from our source. And we're going to update the values of the shortest path so far to those nodes that used to be infinity, but now they are 6 and 7 based on the edges that we've seen so far. We add those to our frontier. So we're going to look at basically every edge that can go out of anything that we've seen so far and check whether that updates our best path so far to that node. So we're going to look at every edge out of 6 and 7. and update that.
I remember this, I remember I did a few questions on this in, with Tony T and data
Mhm.
structures. Really takes me back.
So now we have a value at this third step for every single vertex, which is very nice. But there's no guarantee that just because we've explored each of these edges, now this is the best path, because those edge weights could be negative. What's an example of a path that could be improved from here with an additional iteration? Getting to t can take less than 6. If we go to x, which is 4, and then take the -2 edge from x to t, total cost to t is now 2 and not 6. So just because we at least have a value for each of these vertices does not necessarily mean we're done. So let's show that work. We can look at every edge here, and we're just going to, we can see that we update the value for t at that point. And as we update the value for t, we find that we can improve getting to z.
Yeah.
So one last path here shows that we can update z through that. So when I said from S to Z and said, hey, there's a path with cost 2, that was not the best cost. In fact, going from Y to X to T to Z is the best way to get to Z. And you otherwise would not have seen that with something like Dijkstra's.
Good point.
So let's actually take a look at the code. What are we doing in general? So we're going to say for every vertex in the graph, aside from, of course, the one that we're starting at, we're going to look at each edge that is a member of the edges out of the total graph. We're looking at every edge. We're going to figure out for that edge, does it take us from a node that we've visited to a new node or a node that we've otherwise visited in a way that is better? So we're going to iterate over every edge in the graph and say, does this take us from somewhere we've been with a certain cost? When we reach a destination, does it improve that value? That's what we're going to call relax. We relax an edge, and that says the best possible path we found so far to a source, plus the edges out of that, does that lead to a better path to any destination? So here is what relax really means. If the distance to B is greater than the distance to U plus an edge from U to B, then we're going to update the new best distance to B to be a distance that includes that edge. Take a little bit and take a look at that. It's hopefully this makes sense, but if not, certainly ask some questions. Here's that concept of a relax. We could, before, the best we could do to get to U was a 5. The best we could do to get to a B was a 9. When we relax that, we find that the best path to B is now through U with this edge. We otherwise had not considered this edge after we had updated the best way of getting to U to B5. Maybe the best way we had just gotten to U was 7. 7 plus 2 was the 9 for the B. But when we find a better way to get to U, we can then relax that edge and update the better way to get to U to also involve a better way to get to B via that same edge. Similarly, if you attempt to relax an edge that does not improve the path to the destination, then it doesn't change. So the new best way to get to U is 5, but there's a better just way to get to V that doesn't go through U. The fact that we've now found a better way to get to U does not affect a better way to get to V. So that's just what we mean by relaxing an edge. Just checking, is this a better way to get to the destination when we find a better way to get to the source of that edge? There's a lot on this slide. There's a lot on this slide. Are there any questions on any of this? Show of thumbs. How much sense does this algorithm make? Not as much.
I think it makes sense.
So yeah, we're going to start with the source. The best path we've seen so far is infinity. We haven't looked at any edge. And so we're going to go through every edge and basically say, does the existing value of each of these vertices plus that edge weight lead to an improved way to get to that vertex? Note that infinity minus a value is still infinity. You don't get infinity minus 4 or something that it's still infinity. So the only updates here are going to start by propagating the 0 outwards. This 0 plus 6 is the 6. This 0 plus the 7 is that 7. And that's all we can do with a single pass through these edges and their old weights. So that's all the update we're going to do on the first pass through every edge in the graph, because we're going through every single one. Then once we have the 6 and 7, we can start to look at every other edge out of something that we've seen so far, and we find that we can update additional values, and you just repeatedly iterate through that process until you make no changes. So if we're looking at the efficiency of Bellman Ford, what's the worst case behavior? We have to initialize from the first line. That's going to be V time. We go through every vertex. Then we have the vertex minus 1 passes over the edges. So that's V plus E. We're looking at V adjacency lists to find E edges. Lines 5 through 7, V plus E time again. But that's a loop inside of this. So we end up with the total time here at V squared plus VE. So what order is this in?
This is quadratic.
It would be quadratic in terms of the vertices by this term. VE, remember, depends on whether this is a sparse or a dense graph.
Yeah.
If we have a sparse graph, then E is in the same order as V. So this would also be a quadratic term. But if we have a dense graph, the number of edges are proportional to the vertices squared. So if we're using our main variable here being the number of vertices, then it could be cubic in a dense graph. And remember that Dijkstra's ran in E log V, and E could be as bad as V squared. So in the absolute worst case, this is cubic with respect to V, and Dijkstra's was worst case quadratic log V. So that is better than cubic. And regardless of the graph itself, the type of graph, Dijkstra's will run faster. If we're comparing this to V log V, then whenever this is minimized, then this is V squared, and this would be V log V. V log V is better than V squared in a sparse graph, and in a dense graph, here we have cubic, here we have quadratic log V. And that's better, so nitras will always, for both sparse and dense graphs, perform better. But it's not so much worse that it's intractable. Both of these are very important, useful algorithms to know, and again, the reason you choose one over the other is whether the graph could potentially have negative edge weights or not. Right, that is the time that we have. We will come back on Monday and start looking at minimum spanning trees. It's another algorithm we can run on the graphs. Remember that, please join the Discord. And that's where I'll be posting the study guide later today, since Canvas is down, as well as any updates for things like slides that you'll need to refer to for that. That's also where I'll be posting an eventual assignment.
Okay, is there any work that we're doing the next week?
I think I'm gonna create the cutoff right here. Dijkstra's and Bellman board a little bit. We haven't quite gone through that at the same level of detail. So I will probably won't ask you to break in communication at Bellman.
Will you be in your office?
Yes. Yep, I'll be in my office or office hours for the next couple of hours.
Maybe a set.
Goodbye.
Yeah.
Marvelous.